f of x gets huge without limit, just as I should have said that it's f of x that gets huge without limit here, but in a negative way. Okay, here f of x gets huge without limit as x approaches 3. Denominator's positive, and if x is to the right of 3, x minus 3 will be positive, so you're going to get a big positive number. Now there's more to the graph. We calculated the y-intercept as 0, negative 1/3, and we noted that the function was 0 when x equals negative 1. So we have a point here and a point here. So we know from this point, we got to go through this point and then turn around so we can approach huge negative values. Okay? So the graph has to look something like this. Now what does it look like as you go to the left of negative 1? Does it go up like this? Does it go maybe just touch here and turn around and go down? It could do either for the right function. It could touch here, turn around, go down, and then come back up. But in this case, we consider what happens if x is very large. Okay? In the example I use, if x is 100, then the numerator here would be 101, the denominator would be 997. Now, if somebody offered to give you, I said 97. If somebody offered to give you $97 and somebody half a mile away offered to give you $101, well, you'd be happy to get either, and you'd be about equally happy, wouldn't you? You might not even walk half a mile to get that extra $4 because you're still getting a good chunk of money. Okay? The chunk of money you're getting is about as big. $97 is about as big as $101. So if you divide a numerator that's about the same size as your denominator, if you divide the numerator by the denominator, both numbers about the same size, you're going to get about 1, aren't you? Because if you divide a number by itself, you're going to get 1. If you divide 100 by 97, they're both pretty close, within 4%. Okay? So you're going to be pretty close to 1. I don't really want to use percents because I understand people don't. My experience is most people don't understand percents very well either, unfortunately. So let's not use that, but just let's take the fact that the numbers are close, so their quotient is close to 1. And it doesn't matter if x was a large negative number. If x is negative 100, then you have negative 103 divided into negative 97. Still, numbers that are about the same, actually be 99. The numbers are about the same, so you still get about 1. Well, this is plausible. If you want to make it more plausible, how about 1,000,001 versus 999,997? It's only a difference of 4 out of 1,000,000. Those numbers are practically equal. When you divide them, you get something very, very close to 1. Okay, so the bigger x gets, whether positive or negative, the closer the quotient is going to get to 1. So I draw the line y equals 1 here, and I sketch the graph approaching values y equals 1 to the left and approaching the value y equals 1 to the right. So there is a reasonable picture of this graph. Now, I'm not sure about all the curvatures in here. I could take a bunch of derivatives, find out when they're positive and when they're negative, and figure it all out. But that's calculus. We're not going to talk about that. And you could have that in your future if you do well in your math. Okay. Well, that's an illustration of a very simple rational function. It looks pretty simple, but it does take some thinking. The questions we ask, the things we think about in graphing this function and understanding its behavior are the same as the things we think about when we graph any rational function to understand its behavior. But as you'll see, the rational functions can get longer. The numerators can get, it can be bigger polynomials. So can the denominator. You're still asking the same questions. The answers occur because very similar reasons, for very similar reasons. But you've got to think about a greater number of things. Think about them one at a time, figure out what they do to the graph, and construct your graph, and there you have it.